All right, this is sixth grade, Unit 2, Lesson 3. And in this lesson, students are going to be practicing equivalent ratios, but we're going to be doing it inside some concrete experiences. So they're going to be talking about recipes that taste the same. We're going to be talking about shades of colors that appear the same. So we're going to be using that concrete representation, that concrete experience to understand scaling up equivalent ratios or scaling down equivalent ratios. So let's get started.
All right, we're going to start with a warm-up flower pattern. And the idea is this flower is made up of yellow hexagons, red trapezoids, and green triangles. And we're going to take these figures, and the first thing we need to do is write sentences to describe the ratios of the shapes that make up this pattern. The idea being we could count the yellow hexagons, 1, 2, 3, 4, 5, 6, and the fact that there's two red trapezoids. So we could say that the ratio of yellow hexagons to red trapezoids, yellow to red, is 6 to 2. All right. Now, of course, we could have said a whole bunch of other sentences, but that's just an example of what we're talking about here. And then it says how many of each shape would be in 2 copies of this flower pattern. So, of course, if we used to have 6 yellows, so yellows to reds to greens. So if we're going to have 2 copies of this flower pattern, instead of having 6 yellows, we're going to have 12. Instead of having 2 reds, we're going to have 4. And instead of having, 1, 2, 3, 4, 5, 6, 7, 8, 9, instead of having 9 triangles, we will have 18 triangles. So there you go. All right, so moving down, that was a nice little warm-up. We're going to be talking about a powdered drink mix. And it says, we've got these 3 different mixtures, right? So we're seeing that the white is drink mix and the blue is water. So A is a ratio of 4 to 1. We see that B is also a ratio of 4 to 1. So these are identical mixtures, aren't they? So they would both taste the same because they're the same mixture. But then we've got C, and C looks like it's a different ratio, doesn't it? It's a different mixture. We've got 8 drink mix things, teaspoons of drink mix, and then we have 2 cups of water. So the question is, would these 3 drink mixtures taste the same? Clearly A and B taste the same. So the big question is, how is mixture C, going to taste in comparison to B and A? So we're going to scroll down here, and there we go. We got, there's our ratios again, our mixtures up here. And now let's answer these questions. So how would the taste of mixture A compare to the taste of mixture B? Well, they would be the same, wouldn't they? We kind of talked about that already. And then it says use the diagrams to complete each sentence or each statement. So we're going to start with mixture B uses how many cups of water and teaspoons of drink mix? Well, B is going to use, 1 cup of water and 4 teaspoons of drink mix. So let's do that, 1 to 4. All right. Now the ratio of the cups of water to teaspoons is 1 to 4. So I'm going to zoom in a little bit so that we could see that we would write it as 1 to 4. All right. Of course, we could also write it 1, 2, 4 like that. Right. And so let's keep going here. So the mixture C uses, there's our mixture C way up there. So mixture C uses how many cups of water? 2. And how many teaspoons of drink mix? 8. So we're gonna write that as 2 cups of water, 8 teaspoons of drink mix. And then the ratio of water to teaspoons is 2 to 8. All right, there we go. Then how would the taste of mixture B compared to mixture C? So here's the deal. We see that mixture B, how does mixture B compare to mixture C? Well, we see that mixture B is a ratio of 4 to 1. And we see that mixture C also has that ratio of 4 to 1, because here's 4 teaspoons and 1 cup of water right here. And then we see that here's 4 teaspoons and a cup of water right here. So C is just twice as big, twice as much liquid, I suppose, as mixture B, but they're going to taste the same, because really all we did was we took B and we just doubled the recipe. So they're going to taste the same because they're following that same ratio of drink mix to water. So how would the taste of B compare to the taste of C? Well, they're going to taste the same. All right, good. Now we're going to keep doing it. We've got another one. We've got sports drink with sodium. All right, so where is our sodium? Here is our sodium right here. Oops, I want to do it in yellow. There we go. Oh, okay, I'll do it in red. There's my sodium, and here is my sodium. All right. Now, the interesting thing is it says uses sodium to help replenish those electrolytes. Here are the nutrition, so there's our information. Now we're going to go down, and it says, which of these drinks is saltier? How do you know? So if we're going to look at this, which one is saltier? Well, clearly it looks like this has 150 milligrams where this has 110. But that's 110 for 8 ounces, whereas this is 150 for 12 ounces. So we have to be thinking about how do we compare these two things. So let's see. It was 8 ounces gives us 110, whereas the other one was 12 but 150. All right. So we have to think about, how do we compare these? Well, one of the things we could do is let's see, I'm going to erase that 12 and 150 so that I can scoot it over here, 12 and 150. And we could think about this ratio right here. And just as a recap, that 8 is 8 ounces, and the 110 is 110 milligrams. So if we simplified that ratio, we could see that, that's 4 to 55. 4 ounces of water to 55 milligrams. But then we can triple that recipe. And then all of a sudden, we get 12 and, oh golly, what's 55 times 3? 150, 165. 165 milligrams. So now, in both cases, we have, let's see, I want this. We have 12 and 12, but we now have 165 milligrams of salt compared to 150 grams of salt. So we can now see, scrolling up, we can now see that this one is the saltier one. Oops, there's my L, saltier, because this ratio of 8 to 110 could eventually get renamed to be 12 and 165. And that 165 is way bigger than 150. That's kind of interesting. That's a tricky problem. Parents and teachers, you're going to need to let your students really grapple with this and have fun and struggle. Teachers in particular, the name of the game here is to let them talk and academically discuss this and let your students work on this and grapple and struggle. They do not need to solve it on their own in order to get the most of this. If they work on it but get it wrong, that's okay. They've experienced the idea of trying to compare ratios, and that's really the point. And then you're going to come in and clarify and solidify that understanding. Now, let's see. Question 2 says, if you wanted to make sure a sports drink was less salty than both of the ones given, what ratio of sodium to water would you use? I don't know. It's got to be something less. You could use 12 ounces as your water, but it's got to be less than 150. So maybe we would say it would be 12 ounces of water to 140 milligrams of salt. That would be less salty. All right, batches of cookies. A recipe for one batch of cookies calls for 5 cups of flour and 2 teaspoons of vanilla. So it says draw a diagram. All right, well, we could do that. So we're going to, let's do 5 cups of flour. 1, 2, 3, 4, 5. And I'll just put a little F, 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 and F to represent the flour. And then we have 2 teaspoons of vanilla. So there's our vanilla, and I'll label those with V's. And there you go. Draw a diagram that shows the amount of flour and vanilla needed for 2 batches. So what are we going to do? Well, we're just going to have to do that again. So let's see. Can I do that? Let's see. Can I highlight this? Not really. All right, so I'm going to make that go away. And we're just going to have to do another 1, 2, 3, 4, 5, and then another 2. And there is our model showing how much flour and how much vanilla we would need for 2 batches. There we go. All right, now number 2, question 2 says, how many batches can you make with 15 cups of flour and 6 teaspoons of vanilla? Well, we see we've got 5 flour with 2 vanilla. We've got another 5 flour with 2 vanilla, so that's 10 flours for 4 vanillas. So if we just add another 5 flours, then we're going to have another 2 vanillas. So suddenly we're going to have 5 flours, 1, 2, 3, 4, 5, another 5 flours, 1, 2, 3, 4, 5, and then another 5 flours, 1, 2, 3, 4, 5, and then we're going to have that paired with 2 vanillas, 2 vanillas, and 2 vanillas, and there we go. So how many batches can we make? We can make 3 batches, batch 1, batch 2, and batch 3. The next question, how much flour and vanilla would you need for 5 batches? Well, that's pretty straightforward. That means this is 1, this is 2, this is 3. We're going to need 2 more batches. So we're going to have 5, 10, 15, and then 2 more is 20, 25. So we're going to have, let's draw it. Let's just draw 2 more. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 1, 2. So there's our 5 batches. And where do we see our 5 batches? We see our 5 batches right here. 1, 2, 3, 4, 5. And so how much flour would we need? We would need 5, 10, 15, 20, 25. We would need 25 flours. And then how much vanilla? 2, 4, 6, 8, 10. So 25 to 10. And then the fourth question is whether the ratio of cups of flour to teaspoon is 5 to 2. Whoa, let's see, 5 to 2, to 10 to 4, 15 to 6. The recipes would make cookies that taste the same because they're equivalent ratios. Find another ratio of cups of flour to teaspoons of vanilla that is equivalent to these ratios. So the idea is if we have a ratio of like 5 to 2, then we know like 50 to 20 would taste the same, right? Because those two ratios are equivalent. All we did was take this and make 10 batches right here because this is one batch, so this will be 10 batches. Very good. So how many batches can you make using this new ratio? Oh, I already answered it, didn't I? That's cool. All right, so parents and teachers, the idea here is we are kind of using concrete examples, experiences, to talk about equivalent ratios, things that where the ratio that where the like the recipe is going to taste the same because we've doubled the recipe or we've tripled the recipe, and that's the whole point of this lesson. It's really kind of fun. All right, so let's do a little bit of practice. So here's our classic practice problem. Some of it's going to be new stuff, some of it's going to be review. So a recipe for one batch of spice says combine 3 teaspoons of mustard seeds, 5 teaspoons of chili powder, and 1 teaspoon of salt. How many batches are represented by the diagram? So if 3 teaspoons of mustard seeds is 1, so that's 1. And then it says 5 teaspoons of chili powder. So I'm going to outline that. 1, 2, 3, 4, 5. So there. So this represents one recipe, or one batch, I mean. So here, let's do another one. And I'll circle it in blue. 1, 2, 3, 4, 5. So there. And then lastly, let's do it in green. And then here is our final one. So we can see that we've got, let's see, how many batches? We've got 1 batch, 2 batches, 3 batches. All right. Priya makes chocolate milk by mixing 2 cups of milk and 5 tablespoons of cocoa powder. Draw a diagram that clearly represents 2 batches. So if we're going to be talking about milk, we've got 2 things of milk and 5 things of cocoa. 1, 2, 3, 4, 5. But if we want 2 batches, that means we're going to need another 2 cups of milk, and we're going to need 5 tablespoons of cocoa. So there is our diagram showing 2 batches. All right. In a recipe for fizzy grape juice, the ratio of cups of sparkling water to cups of grape juice is 3 to 1. So water to concentrate is 3 to 1. Find 2 more ratios of cups of sparkling water to cups of juice. That would make the mixture taste the same. So we could take that batch, and if we double it, we would get, we would get 6 to 2. That makes 2 batches. And then if we were to take this recipe and do 3 batches, we would get 9 to 3. And if we wanted even 1 more, we could do 12 to 4. All right? And we should be looking for patterns, right? We should be looking for neat little patterns in these equivalent ratios. So be on the lookout for that, parents, teachers, students. So describe another mixture of sparkling water and grape juice that would taste, that would taste different than this recipe. So really all we have to do is choose any of these to make sure it's different. We could choose any of them. That 9 to 3 is a good one. But then cross off the 3 and make it an 8. Or make it any number other than 3. And that will definitely be different. All right, write the missing number under each tick mark of the number line. All right, so, oh my goodness. So if we're going from 18 to 30 and then 30 to 42, how are we growing? So in my mind, I'm going to be thinking about the fact that Okay, so we're 12 apart, and there's 2 jumps. So it feels like we're adding by 6. So 18 plus 6 is 24. 24 plus 6 is 30. So 30 plus 6 is 36. And then 36 plus 6 is 42. So there you go. There you go. Got it. Nice. And number 5, at the kennel, there are 6 dogs for every 5 cats. So the ratio of dogs to cats is 6 to 5. The ratio of cats to dogs is 5 to 6. For every 6 dogs, there are 5 cats. And then lastly, the ratio of cats to dogs is 5 to 6. All right. Number 6. Elena has 80 unit cubes. What is the volume of the largest cube she could build? The largest cube, right? So remember, a cube is that 3-dimensional figure where the edges are all the same, and we need this number, and this number to be the same, and they're going to multiply to be something no larger than 80. So I don't know. Let's see. 4 times 4 times 4 is 64, and that would be cubic units. Let's try 5. 5 times 5 times 5. Well, that's 125 cubic units. So that is too big. So what is the largest cube? It's going to be a 4 by 4 by 4 figure. So those x's are actually 4s. And last one. Fill in the blanks to make each equation true. Let's see. 3 times a third, well, that's going to be 3/3, which is 1 whole. So 10 times a tenth, that's 10 tenths, which is 1 whole. 19 times a 19th is 1 whole. Ooh, a times a eighth. 1/8. That's funny. 1 over a. So the idea is we should be seeing a pattern. 3 over 3 is 1. 10 over 10 is 1. 19 over 19 is 1. So a over a is 1. All right. And really, as long as a does not equal 0, that's because you can never divide by 0. Very good. All right, and then scooching way over here, 5 times what is 1? Well, we should be seeing the pattern over here, shouldn't we? And so this is 1/5, this is 1/17, and this is 1 over b, not to be confused with a 6. So there you go. We're looking for patterns there.
All right, and that wraps up a fun one. It was grade 6, unit 2, lesson 3, where students were experiencing equivalent ratios, scaling up, scaling down in a concrete experience.